Hello everyone, it's February 26th. So I just watched a video of Primogen reacts to Linus' reaction to some code. Basically the gist is do not solve problems that does not exist yet, and definitely do not do the dry principle on every single thing. I am I commit this fault from time to time. I know, always trying to maybe I can wrap it in another layer, right? I can write a wrapper on top of this and another wrapper on top of this. It's most commonly it's like APIs, right? You have some API now, write a wrapper on top of the API. Just this type of thing needs to stop. Exactly, this type of thing needs to stop. Some of them has reasons that I do, because I'm thinking about like I was in Firebase, right? And Firebase has their SDK that can connect and then do data manipulation on Firestore. But I want a way to call these APIs from anywhere, right? From anywhere, and then I write an API on top of, basically on top of the SDK. I don't know, like is this considered a good practice or not a good practice? I have no idea. Basically I have no idea. I feel like it's a good practice because I am exposing the Firestore SDK too, so you can use it anywhere. But on hindsight, I think that might not be a good idea at all, because the Firebase SDK is already a wrapper, right? It's a wrapper on top of some other things, and then I'm writing another wrapper on top of it. It just doesn't make any sense, right? It does not make any sense. And if we need to develop a web app that accesses Firebase, then we should, instead of providing these APIs, we should just use the SDK directly, right? You can save one layer of complexity on this. Yeah. And the example that Primogen pointed out is, very, I can see myself doing it. It's just like you have Docker and you have whatever command you need to run in Docker, and you're like, I don't want to type so much things. I just want a wrapper on top of all the Docker commands. I mean, you just think about it, right? As you say this out loud, it sounds absolutely crazy. This needs to stop, right? This needs to stop. Yeah, I have a tendency to do this thing. I'm definitely needs to stop doing it. Not everything needs a wrapper, right? Not everything needs to be dry. Sometimes you can repeat, because the use case for a dry solution has not risen yet. And if it has not risen yet, do not predict, okay? Do not think you have a crystal ball and you can predict a future use case, and then you just pile tons and tons of, oh, what if this happened? And what if that happened? No, don't do it. Do not do it, all right? You do this type of thing when the use case requires it. If the use case is not required, don't do it yet, right? Don't do it yet. Just don't do it. You can write a condition and just say, no, we just don't do it. Yeah, it's absolutely, absolutely. It's great advice. All right, so we want to check if the two are the same. That's all right. It's all right. Oopsie doozy. That's not what we want. We want to do a Java version 26. Oh my god. My fat finger is absolutely bonkers. You are so stupid sometimes. It should be 26.java. Yeah, I changed. I'm just gonna go full screen on this, man. Sorry. Sorry if you cannot handle this. I'm just gonna go full screen on this. Otherwise, yeah, it hurts my eye, you know, it hurts my eye. I need to go full screen on this. Alright, so what we want to do is we want to check if the two trees are exactly the same. So we can say if not. So we say if not P, okay, and not Q, right? That will return true. Right, and if P and Q, right, then we can return P dot val equal to Q dot val and is same tree P dot left, right, Q dot left. Oh, that's not right. Where am I? 36 dot left and 3 and is same tree P dot right, Q dot right, right? Oh, it can be one line. So we don't do this, and I return false. Something like this. Probably you have to do. No, I thought that I can do it. Well, I think that's Python's syntax. Oh my god. So you have to constantly switching language. Oh my god. Yeah, I can't do it. I cannot do it. I still have all the Python stuff in my head. Thank Lord we tested this. Alright, so what do we say? We don't say anything. We simply just call it a day, and not call it a day, just finish this, right? And we move on to this problem. We say we're gonna try Dijkstra and Bellman-Ford. Okay, so now we're gonna try Dijkstra. So for Dijkstra, I said it's actually a k-stepped Dijkstra, right? It's a k-stepped Dijkstra. So what we want is definitely want to create. I have no intention to write Java again. Oh my god. We have to create a tree, the graph. Man. Yeah, we have to create a graph, and then we have to create the okay, let's calm down, and then we're gonna do it. We will do it. I don't remember. It's like what, 20? When was this? 23. Find cheapest prices. Find the cheapest price? Yes, find cheapest price. All right. Okay, well, I might copy. I might steal something from here. You know? Seriously, I'm gonna steal something from here. Not all of them, but definitely I'm gonna steal, so I don't have to do as much. This is gonna be 2, right? We can do this, and these are fine. Okay, these are fine. All right. The prices. I'm pretty sure for the prices, it's just gonna be instead of doing this, lowest price to reach node I, right? So because of this, we only need to do n, because we have n nodes. Okay, and then we can say array stuff fill prices with max. Okay, and then we have the list. It's a queue, right? So it has to be a priority queue. Okay, priority queue equals to new priority queue. Good. So each element is node and step. Okay, node and step. Okay, so queue.add, and I probably need to also say prices source is equal to 0, right? And this is the 0 step, right? 0 step, we don't need this. And then while not queue, and then this is gonna be, you can say Dijkstra, while this, and that's fine. And we don't do this. We simply say check the top, right, with the price. Yeah, check the top with the price, and cannot be longer than k, right? Cannot be longer than k. So I will say while it's fine. We pop it out. Okay, we pop it out, and then we say int element equal to queue.poll. Okay, and then we say int node equal to element 0, and int step is element 1. Okay, be more explicit. If step is if stack is equal to k, then we simply cannot keep going, right? So we say if step is, well, that's actually if a step is larger than k, larger than k, I probably won't even put it inside. That is a good point. I mean, I will do something. If it's not, I won't even put it in. So I can guarantee that a step is smaller or equal to k. Okay. So if you can guarantee that, then what I do is I just check. I say node, if it's equal to destination, right? And say the first time we can reach destination, I think that is when we return the price. Because we want to return the price, and then we have reached it, and we're not return the price. So prices destination, right? And otherwise, not otherwise, then we don't do this. We will do, oh, but what about the current price? So it's actually, we do need price, man. We do need price. We need a current price, and we need step. Okay, so we need 3 things. So int current price is element 1, and this is gonna be this will be 2, right? And again, if node is this, then I just return current price. I don't have to do this, I just return current price. And in fact, I should first say if current price is not equal to prices node, then I continue. Okay, then I say if node is equal to destination, that we're already done, right? And then we can delete all this d3j, right? We delete this. Does Java has a formatter? I wonder. And then we're gonna do child element child edge cost, and then we shall say if step plus 1 is smaller or equal to k, and the new is current price plus edge cost is smaller than price's child. If this is true, then I will update price's child equal to current price plus edge cost. Yeah, I like to do it here, which usually is not where people usually want to do. So it would be q dot add new int. Oh, we need 3 things, my bad. So we need another 0 here, right? So here we have the node, and price is going to be current price plus edge cost. Oh my gosh, you do it 3 times, man, 3 times. So next cost, next price, right? So we this plus current price. That's not what we want. Can we go back here? Oh, no, that's not what we want. Go down. Let's go to 40. No, we have down more. Okay, where are we? So we say we want this. So this plus current price, right? Then all of this can be deleted, become next price, right? And then this is also next price, and this is next price, and step plus 1. Right, we add this, we don't need this, we don't need this, we don't need this. Yeah, we just step plus 1, and then keep adding if the step is right, and then we can do this, and we just keep adding, and then we go back up, and then we do all this, and eventually, if we do not return earlier, then we just return -1 here. Okay, so that's my other solution. Okay, let's give it a shot. Let's see if it's right. It's like case step. A k-step Dijkstra. Oh my god. We wait. Alright, is this one correct? What the hell? So I need to do a comparable. Oh my god. So what we're saying is Java priority queue comparator. How do I use? Yeah. I need a comparator. Do we have a simpler version? New this what is the first thing? Is the length? Can I not do the capacity? Initial capacity. Well, I guess you can put whatever, right? Alright, so yeah, apparently you cannot do it this way because it's complaining. Comparable is not. Alright, so I have to do is capacity. Let's put, I don't know, put 5 capacity, and then we say element 1, element 2, this is a lambda expression, and then we say integer dot compare. I don't know, is that correct? E2 0, because we want a min heap, right? No, it's not 0, dude. It's a price the second one, so it should be 1. Does this work? It does not work. Oh, this is not no, this is a child. Okay, let's just focus on the first test case. I mean, my theory is once the step is too much, then I just quit, right? I just quit. So every time I pull with the current smallest, actually I need to just see, right? I need to see sys dot out dot print system dot out, right? System dot out dot print line. I need to know the node, current node, and it's just debugger. I don't have a debugger, man. Okay, I just have to repeat this 3 times. Probably also to do this so I can know. I need to set up debugger. There's no question about it. I need to set up this in it as well. So we have 0, 0, 0, and now we have 1. 100 is 1. Wait, what? Wait, what's the destination? Destination is 3. And I just AND. And my K is 1. Ooh, 1 stop, right? Oh, hold on. 1 stop. Therefore, this is a 0 stop, right? This is a 1 stop. And, so we do this. Because I allow this to +1 one more time, right? I allow this to +1. Which means this step, because that's the number of nodes in between, right? If the number of nodes in between is smaller or equal to k, I'm okay with it. Because the next one, if it is the target, then it will be fine. It will be fine. So now we try this and it should give us the right answer. Okay. So I have some confidence and let me write stuff at the top. So this one basically is Dijkstra case step. So Dijkstra, right? Dijkstra with at most k stops between source and a destination. Oof, a little bit nervous, but I think I have this very big test case. So I think it should be fine. And it's not fine. Damn it. Okay, so yeah, let's take a look. We have 4 nodes. Wait, how many test cases did we pass? 43. Was this one of the error one in the past? No, it was not. I don't think so. But anyway, so we have from, to, and price. Okay, so we have 0 to 1 with 1 price. 0 to 2 with 5 price, 1 to 2 with 1 price, 2 to 3 with 1 price. What else? That's it. So we start from 0 and end at 3. So we start from 0 and at 3 with k equal to 1, only one stop. So from 0 to 3, I do have 1. Okay, so what happened? So in our case, we start from 0 and, oh, it's always pointing this way. And then it's 1 point into 2, and then 2 point into 3. Okay. So from 0, I get 1 and 2, and then I'm at 1 because it has smaller. From 1, I'll get to 2. Okay. And so that's already one stop. And from 2, I cannot get to 3 because that's the end, right? I cannot get to 3. There's no way. Oh, because I think I simply popped it. Oh, I see the problem. Because I already set the price to 2 is 2, right? The price to 2 is 2. What are you saying now? What are you saying? What I'm saying is, if you reset, stops, right? Stop. If you hit something and then you re-hit it, then your stop needs to change. I do have stop, right? I do have stop. And so what you're saying is the prices needs to be also take into consideration this number of stops. I don't know about that, man. I think what I can do is, if the step is larger, then yeah, because I'm reaching this 2, right? This 2, the stop become 2, right? Stop become 2, and stop is larger than k. So we probably can say elif else if, or maybe just else, right? If the current price is larger than, we just ignore it. And if the steps are smaller, equal to k. Yeah, we should say elif step is larger than k. So in that case, I'm just guessing. In that case, we have, basically we say we cannot reach this node, right? It's not possible. So we need to reset its price to this child. We reset to max. Okay, if we reset it to max, then nope, the first one doesn't work. How about the last one? The last one doesn't work either. So still, that's not right. We cannot reset it to max. Oh, because the current price, I check it to be not equal to the prices. So do I not handle that? Yeah, that's not right. Doesn't feel right to me. Yeah, so we walk to a node that is not correct. Okay, we walk to a node that is not correct, and I need to reset the value. And then as I go, yeah, this is hard to see. Or maybe because I reset to max, and we say if this is not equal to this, and we can say and prices node is not equal to max. If prices node is equal to max, what we say is it's Oh, hey, hello. Wow, I mean, this problem, I solved it before already. I'm just trying to see if I can use Dijkstra to do it. My previous solution was a BFS, a straight up BFS, and it works. BFS works. I'm just trying to see if Dijkstra can work. Well, I shouldn't say I'm trying to see because I know Dijkstra works because the solution in 2023, about more than a year ago, it was one of them was Dijkstra. So I know Dijkstra works, but I'm just trying to figure out again how to do this in Dijkstra. Yeah, so I'm kind of resetting the price, and I just say if it's not equal to the max, which means it has been handled before, and I say then it would just be bad. Okay, let's try this. But if it is max, I would just keep going. Ugh, still. So everything is right except for the last one. So this is still having problem. Okay, but anyway, when we go here, what we have is we're heading at the 2, right? So k steps is equal to 2. Steps is equal to 2. And because at the beginning, okay, 0, I have 1. And steps is smaller than this. Yes, small equal to this. Okay, so yeah, this will equal to this. So I set the 2 at the first round. I set the 2 to 5, right? And then next one is this one pop out. And this one I push in here, and then I reset the value for 2 into the max, right? And now in the queue, I basically have 2 versions of this. I have 2 versions of this. One version is the previous 5, and the other version is, I do not have the other version. I just have the previous version. So I'm expecting the next one to come should be 2, right? With price 5 and step is 1. And then I shall be able to push 3 into it. All right, we'll have to do this one more time. Oh, I hate it. I had this before. And I have to redo it. The print line. So print node. We need to print current price. We need to print element. Step. And then what we need to do is to print a separator. All right. Oh no. I don't want to run all of them. Damn it. I just want to run one of them. Okay. I'm using graph. It was not dynamic programming. It's just a graph. It's just a graph problem. It's not really that hard. And so yeah, but okay. Anyway, so let's see. So we have 0, 0, 0, and then we go to 1, 1, 1, which is correct. And then we go to 2, 2, 2, 2, 2, 2, right? There's a 2, 2, 2, and we fail. So the next one come out is 2, 5, 1. That is correct, right here. 2, 5, 1, and I shouldn't continue because only these 2 will continue. Dude, I need to keep printing. Okay, this is not enough. I need to know more. So what I need to know is prices node. Okay, I need to know prices node. Let's see what the prices node at the moment. 0, 1, 2. It says it's 2. That is bonkers because I thought I reset it. Right? I did not reset it? I mean, okay, so when we have this 2, 2, 2, right? So I have 2, 2, 2, everything is 2. And, oh, everything is 2. I see. Ugh. Okay. I know the problem. It's just when we set. I have my way of doing it, and it's really pissing me off at the moment. So what we should do is to move something earlier. Okay, to move something earlier. So the current. The current price and the current element. We can do some comparison. Okay, and then when we move on to the next one, if step is smaller than k, all right, it'll be like this. If step is smaller than k, perfect. Then I do this. If step is equal to k, and step is equal to k, and it's not. See, that was the problem, right? It's equal to k, but it's not the destination. Then you need to reset, right? Then you need to reset, and you don't push the next one. Oh, it's great. How was university going? All right, step. Oh my God, how am I supposed to handle it? It will be so complicated here. I wish I could move it up, but I don't want to move it up. Okay, so it's fine. So we say if step is smaller than k, then we do everything, right? If step is equal to k, then we need to check if it's the target. If it is the target, then we return it. If it is not the target, then we need to set its price. Okay. Which means I will not do it here. Okay, I will not do it here. I will check it here. Child next price. Okay, so if this is smaller than k and next price is smaller than this, I do this. Perfect. L if it is equal to k. Okay, if it's equal to k, then we say if. That's great. Great to hear that. Yeah, great to hear that you're doing well. Yeah, college was a long time for me. All right, so anyway, so if the step is equal to k, now we need to check. If the child is equal to, if child is equal to your destination, yeah, I want to return right here. If child is equal to destination, then we can return, we shall return right? Is that right? If child is equal to destination, then we shall return. It depends. No, like it because we are Dijkstra it until this point, and yeah, I really shouldn't do it here. What should I do? What should I do? If step is smaller or equal to k, okay, if it's smaller or equal to k, I do this, but when I push, I shall say if if step is equal to k and child is not equal to destination, in that case I will reset the child price equal to max. I'll reset to max. This basically is an impossible case, and I don't push the child into it anymore because there's no point, right? So the child is already wrong. But else if it's else, then we can do that. So we have this. Okay, let's give this a shot, and then I basically do the same thing as before. Right, we do the same thing as before, and we don't do this. And we have to say here as well, if node is equal to destination, then I return price, current price. All right, is this one right? Okay, this one is good so far. Let me gather all the test case again. Okay, all the test case seem to be working. All right, let me delete this again. Okay, so yeah, we have this little, there's a reset, right? Reset the price for unreachable node. All right, come on, show me some. Oh my god, that's still not right. What's the problem now? Why is it so hard to get a Dijkstra working for this? This is unbelievable. All right, let's try. So we have 0 to 1 is 5. Okay, 1 to 2 is 5. 0 to 3 is 2. 3 to 1 is 2. Okay, 3 to 1 is 2. 1 to 4 is 1. 4 to 2 is 1. So we go from 0 to 2 with 2 stops. So we go from 0 to 2 with 2 stops. Yeah, here we go again. It just wrong again. Unbelievable. Okay, where did we go wrong on this time? So from 0, expected 7. So we have to go from 0 to 2. 7. Oh, so we go this, and this. 2 is 4. 5. Is that 6? Wait, did I do it wrong? 0, 1, 5. 1 to 2 is 5. 0 to 3 is 2. 3 to 1 is 2. 1 to 4 is 1. 4 to 2 is 1. How is expected is 7? Oh, 2 steps. Oh, 0, 1, 1, 4, and a 4, 2. All right. Let's take a look. No, I'm definitely not a competitive programmer. I wish. I think I tried that for some time, but it didn't work because just not capable. It's a skill issue. And you have to invest quite a lot of time into it, and definitely I'm not at that level anymore. Like this, right? It's such an easy one. This is a very easy problem, but for whatever reason, I've been struggling to find a solution through Dijkstra. Anyway, so we start from 0 and then we go to 3. Yeah, we go to 3, and then we go to 1. That's understandable. And then 1 we go to 4. We don't go to 4 because I try. So because here we try to go to 4, but it does not work because I already have 2 stops and this is not the destination, so we don't do. And then the next one come up is 1 again with 5. Okay, 1 again with 5. Oh, I need to reset it, right? Damn. Okay, so I have to use a 2D array. But the thing is, yeah, I'm just improving, and it's a hobby, you know. I like doing it. All right, I'm gonna check because here I remember better Dijkstra, city and number of stops. Okay, I have some city and number of stops. Huh. I'm basically checking the solution. City and number of stops. Use the traditional Dijkstra but without keeping track of the distance. This is because if the optimal way fails, we can continue with the suboptimal way that is already in the queue. The trick to avoid cycles is to keep track of the number of stops to reach each city. If we have to reach the city again, it must be with fewer stops. Otherwise, the result won't be better than the previous. That is correct. Then why do you use Dijkstra then? Oh, because each time still the lowest price come up first. But then I don't keep track of the price because each time we have a new stop, you will have to restart. So basically this says if I have visited this thing with fewer stops, then I will continue. Because because if I can reach it with fewer stops before, and that must mean it has a lower price. Or if stops is larger than k plus 1, and with this, look at that. Look at that. All right, let me get back here. There's a lot of things I need to change. Hold a second. Let me change this. Okay, so what I want is it's not prices. Okay, so this is stops, right? This is what we want to do, is do stops. It's not lowest price. This is we're gonna return is the number of stops to reach node I. And yeah, we can set it to maximum. Yeah, we can do this. That's fine. So the stops, right? Number of stops to reach, and then this is node price step. Shall call it stop. Shall call it stop. So all the step becomes stop. My God. Okay, so all the step becomes stop. And now we do this, so we get an element, we get a node price stop. And then when do we continue? Well, we continue if, actually, we can just do it here. We continue if current stops is larger than k plus 1. That's actually true because the stops can be k, right? Stops can be k. They can check, right? And yeah, stops can be k, but stop can also be k plus 1. Yes, the stops can be k plus 1 because if stops are k plus 1 and your node is destination, yeah, that's still okay. So if stops is this, or another situation that you need to continue is I have visited already, right? So basically we say the current stop is larger than previous stop, or larger equal to, right? Previous stops node. This just means if wait, what? The operator is undefined for the argument type. Int. Huh? What are you talking about? Oh, here. This is not stops. This is stop. Right? We say if the current stop to reach is larger than before, so basically we say we can reach it with fewer stops. Yeah. If we can reach it with fewer stops, then okay, so we can do this and we do this. And then for child, blah, 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 we do this and next price. And we just push it in. Right, we say q add new int child next price and stop plus 1. Okay, give this a shot. Not sure. Oh, this now prices and stops. No? Wait, what did I do wrong? Yeah, if stop is larger, right? If stops is larger. Oh, stops is larger. Okay, I need to write something here. So, if the current stop, right, is k plus 1, there is still a chance, right, that the current node is the destination. So the condition must be stop larger than k plus 1. And also, if we have visited the node before with fewer stops, right? Having more stops now will definitely not help, right? Will definitely not help the case, not help bringing down. Thus, we skip this condition. We skip BFS, right? If that is the case. And then we do this, and then we do this. But when did we update the stops node? I need to update that. Right? I need to update that. Well, what we should do is we shall update it right. Yeah, I never update the stops. Where should I update it? This is the next price. This is to go for the next stop, right? And we shall update it right here. If the stop is smaller than this, then we shall, yeah, I think we shall update the stop. Say stops node shall equal to stop. I hope it's still correct. All right, let me run one more round of testing. This one should be right. I said I basically copy and paste my previous solution. Still pretty bad. Okay. Basically, copy and paste my solution from a year ago. So the key idea, yeah, it's the same. It's the same complexity and everything. The key idea here is do not keep track of the price, right? Do not keep track of the price, because Dijkstra, what does Dijkstra do? Dijkstra will always get to a destination with the lowest, whatever you put in there, right? With the lowest cost, always. And what we're doing here is we put a constraint on how many stops we can allow. Therefore, the first time when Dijkstra reaches the destination might not be the answer, right? But the beauty of Dijkstra is if you skip that one, like you just don't do the wrong one and you just keep searching, and every time when Dijkstra does the search, when it reaches your destination, then your destination will always be having the lowest price under whatever the current situation is. So all you need to constrain is the situation, which is exactly this line. This line we control the situation, right? We control the situation based on the stop, and everything else is just, it's just Dijkstra. You don't have to keep track of the price. It does not matter, because each time it runs, right, you always get to the lowest price, right? You always have the lowest price under the current situation. That was good, right? That was good. That is the idea. Okay. So for a question like this, I like to do it again because it definitely requires more effort. So I'm just gonna cancel it, and I'm even going to remove this. So I can, hold on, why it doesn't work? Alright, so we remove this. The whole point for all this practice is just to keep practicing. And I'm definitely having trouble with Dijkstra in this one, so we're gonna practice again. And I'm gonna close this, so next time I cannot see. Okay, let me just take a look at the Bellman-Ford. I forgot what Bellman-Ford is. What is Bellman-Ford? It's like flow, right? What does it do? Price. Source is this. This is the number of steps. We have a temp. Temp source equal to 0. We go through every single, what the hell is this? We go through every single edge. Oh, we go through every single edge. A, B, and price. And temp B is the minimum, so we find temp B. Price is B. Price is B. Okay. Price is B. And price is A plus P. What the hell is this? Oh, now I cannot see it. Wait, what is this? Bellman-Ford. Bellman-Ford. What does it do? Imagine you have a map with different cities connected by roads, each road having a certain distance. The Bellman-Ford algorithm is like a guide that helps you find the shortest path from one city to all other cities, even if some roads have negative length. It's like a GPS for computers, useful for figuring out the quickest way to get from one point to another in a network. In this article, we'll take a closer. Okay, Bellman-Ford. Single source shortest path algorithm determines the shortest path between a given source vertex and every other vertex in a graph. Guaranteed to find a shortest path fast, similar to Dijkstra. It's slower than Dijkstra. It is capable of handling graph with negative edge weights, which makes it more versatile. Shortest path can be found if there exists a negative cycle in the graph. If we continue to go around the negative cycle an infinite number of times, the cost of path will continue to decrease. Yeah, I think that's the okay. The idea behind starts with a single source to calculate the distance to each. You start with a single source and you calculate the distance to each node. The distance is initially unknown and assumed to be infinite, but as time goes on, the algorithm relaxes those paths by identifying a few shorter paths. Hence, it is said based on principle of relaxation. All the edges should be relaxed n-1 times in order to detect whether the negative cycle. I don't want to know about negative cycle. Just show me. Just show me. Why you kept talking about negative cycle though? But anyway, we can use this to see how it works. So we have the source, right? Initialize distance array to show the shortest distance to each vertex from the source. Initially, distance of source will be 0 and distance to all the others infinite. Okay. Start relaxing the edge. During first relaxation, current distance B is larger than distance A plus the weight. Therefore, distance B is 5. And that's it. During the second relaxation, current distance D, that'll be 7, this will be 6. Okay, so well, we can move here. And the next one, we need to move to E, right? So, no, we first go to F. Oh, there's no going to E. So we'll go to F and then go to E. I agree, that's fine. And then F need to go to now we go back up. So this will be 6. And then EF come to E. E becomes 6 as well. During the fifth iteration, current distance F will become, sorry, plus, right? So become 8. Current distance D should be 5. Since the graph, so during the fifth relaxation, the shortest distance for all should have been calculated. Really? You only go... Oh, really? Now the final relaxation, the sixth iteration should indicate the presence of a negative cycle if there is any changes in the distance array of fifth during the sixth relaxation. E to F. Huh? Wait, that's fifth relaxation, right? It should be F to E. Distance. So E become 5 and F become 7. Since observed changes, we can conclude the presence of a negative cycle. DEF. DFE is a negative cycle because it all gets more and more negative, more and more negative. Okay. Interesting. So the Bellman-Ford is you start from the root and then you just keep going, right? You go out and then you, but look at the implementation here. I go through every single thing. I go through every single thing. And yeah, I mean, it's understandable. We go through every single thing. But it seems like the other one suggests it's more like a BFS. You have nodes and stuff, right? You're pushing into a queue. But this one's not. This one, you just, every time we try, and it makes sense, right? And it makes sense. We just simply go k times, right? We go k times, and well, technically k minus k plus 1 times, right? We go that many times, and we just try to see, if I go that many times, what is the minimum price that a destination can be. That is the Bellman Ford. Because at each step, I basically just update. Yes, at each step, I update the price of each node. I don't even care. I just go. Very interesting. Very interesting. All right, that will be it. So I hope tomorrow we're gonna hit this problem one more time. Okay, I don't care. We're gonna hit this problem one more time tomorrow, and hopefully I can also use the Bellman Ford. Where are my other problems? Oh yeah, I solved this one. This is the problem. Oh my god. All right. Anyway, I'll end it right here, and I will see you guys tomorrow.